Welcome to our course. I'm interested in biodegradation here. We'll just do a little bit of a summary, a start of this subject. So, what is biodegradation? That's already a problem, and it's usually a question that I ask my students, and we usually discover that it's not that easy to say. Why is that? Well, we expect it's degradation by bio, but if we look at the official definition, it says you have to throw something, your target material, into a compost heap, and you wait for a certain amount of time. It's about a month in the case of the European regulations, and if it's broken down to a small enough size that it goes through a sieve and you can't find it, it's considered to be biodegradable. But that doesn't necessarily mean that the biology has degraded it. If we put a piece of salt into a compost heap, a block of salt into a compost heap, it's wet, it's going to dissolve. So you won't be able to sieve it out after a month. It hasn't biodegraded. It's still salt. But it would pass the test if that was the only test that we had. So it's not that easy to make a test. What about if we consider something that is normally thought to be not biodegradable? If we look on the internet and we look at polymers, they're considered to be not biodegradable. But most polymers will degrade in interaction with bacteria over time. It's just a very long time. One of the polymers that is of particular interest is PET, the type of polymer used for drinking bottles very often. It degrades in the light, and it's not very biodegradable. It takes a long time to degrade. It wouldn't go in 21 days. It wouldn't go in 6 months. But it does degrade in biological environments, and there is a sort of weapon. There is a way of making bacteria. There are some bacteria that are particularly good at degrading polyethylene terephthalate, PET. So if we wait long enough, we can break it down. Let's take another example of a chemical that you would expect to not be broken down by biology. So if we take trichlorophenol, TCP, so this molecule, Cl. If we take trichlorophenol and we throw it into the environment, which people have been doing for years, it's a sort of broad spectrum disinfectant, particularly interesting at these times of corona. So, trichlorophenol, OH. Need to check that. But if we take this trichlorophenol, which is actually a broad spectrum disinfectant, it is eventually broken down in the environment. It takes a long time, but it is eventually broken down in the environment in special conditions. It's quite difficult to get these chlorines off, but there are conditions under which they can be removed, and then the ring becomes part of the environment. It is absorbed into normal biological processes. Obviously, or not obviously, but biology doesn't really know what to do with these chlorine groups on the side. Most organic compounds that are natural don't have halogens on. What if we take another material? If we take iron, if we look at iron and we leave it for a really long time, it will corrode away. So if we take a piece of block of iron and we throw it somewhere, it will eventually corrode away. If we put it into compost and it's small enough, it will disappear. Has it biodegraded? Sort of. If we put it not into contact with the bacteria, it will corrode on its own. And if it's in contact with bacteria, it will corrode slightly faster because the bacteria release chemicals and they use up the iron dissolved in the water, so they can make it corrode faster. What about printers. The printer cable, the biodegradable printer cable is made out of polylactic acid. However, polylactic acid is not stable anyway. Polylactic acid breaks down in the environment by hydrolysis. It doesn't need any biology to break it down. If you leave it lying around for long enough, it converts into lactic acid on its own. It will break down, it will hydrolyze. It doesn't actually need biology. Biology speeds it up, but it would normally degrade on its own. How much of it is biodegradation? Some of it is, some of it isn't. It's also a good example because if we take bags made out of polylactic acid mixed with other things, it will typically say on them compostable, but if they're being honest about it, it will say not for home compost. So if any of you have that experience, if you throw a compostable plastic bag into a home compost heap, typically nothing happens. That's because polylactic acid, for example, it's not the only one. They're usually a mixture of different things. Polylactic acid is quite resistant, does biodegrade, but it doesn't biodegrade very fast until it gets warm enough for it till it reaches its glass transition point, effectively, which you'll know from another course. The others of you, it needs the parts of the molecule to move around so that enzymes can get there to cut where they normally would cut, and very often inside a block of polymer, most of the places to cut it are hidden inside, and it will be very slow. It's got to nibble from the ends and to erode it very slowly. If it's warm enough, it can move around, the molecules inside can move around and be degraded faster at the surface. In that case, it's I believe it's 65 degrees. Above that, polylactic acid biodegrades very much faster than below it. So if we want to get rid of the polylactic acid, if we want to get rid of some of these biodegradable compostable polymers, they have to be in a hot compost heap at above 65 degrees, which some of the industrial ones are. The typical industrial composting process runs at a much higher temperature than a home one, and that has several advantages. Firstly, it kills seeds and fungi, which is a good thing, because we don't want to grow tomatoes and potatoes every year like we do from my compost heap. What we want to do is have compost to grow whatever is that we choose to grow, and not just seeds that are in there. So we would like it to run at a high temperature. That's good. It also means that some of these polymers will degrade at a reasonable time scale, whereas normally they take a very long time indeed. So there is a problem with biodegradation, because we could say a very large number of chemicals will biodegrade if we give them enough time. And there's another problem with biodegradation, which is what conditions are we going to do it in, which are very difficult to define. So if we look in the European regulations, there is a lot of talk of a normal compost heap. What is a normal compost heap? We've already established that an industrial compost heap runs at a high temperature, and it is much more effective at some things than a home compost heap. And if you ever run compost yourself, sometimes it works and sometimes it takes a really long time. Sometimes you open your compost heap and it looks like nothing has happened for 6 months. Very often here, that's in the winter when it's too cold and nothing happens. But very often it's because it's got too much of one thing or another in it. And so these industrial composting places, the biogas places that make methane, or they make energy effectively from biological waste, typically farming waste, they have to control very carefully the concentration of carbon and the concentration of nitrogen, or the ratio between carbon and nitrogen in their feedstock, because that determines very much what you get, how fast it runs, how much side products you get, what bad things happen, what good things happen. So it is very, very varied. How fast we will break things down is determined by what kind of compost heap we have and what the temperature is, what the pH is, how much water is there, all kinds of things. So if we try to sum that up, if we have something that, for example, polylactic acid, very often we will see it biodegrades, but it also is affected by some other chemical process. In the case of polylactic acid, it's hydrolysis, so it's broken by water. We will draw that. PET, for example, also hydrolyzes. It biodegrades, but it's much more slow, and so it falls outside the definition that is used in European law, but that doesn't mean it doesn't biodegrade. It biodegrades fast enough to be a problem if you try to make something out of PET and keep it in your garden. Iron is also affected by bacteria, but can we call that biodegradation? It's difficult because it's not really, they're not really using enzymes to attack the iron itself. It's a side product. They are really making acid. It's the same as the things that the bacteria that attack our teeth. They make acid. They're not really doing it to break the teeth. They don't really care about your teeth. What they want to do is convert sugars into food for themselves, into energy, and the side product of that is acid, and the acid attacks the iron or your teeth. If we take the other extreme, at very long time scales, even some ridiculously resistant chemicals that are nominally not biodegradable are actually degraded by biology. So if we take chlorinated hydrocarbons or polyaromatic hydrocarbons, so if we take something like naphthalene, which has two fused benzene rings, it's a bad chemical. It's formed in tar production. It's formed accidentally when you burn things. It's considered to be really bad. It's very persistent pollutant and it's quite toxic, but if it hangs around for long enough, it will be broken down by biology and in various ways. And there are many pathways to get rid of things which are managed to get rid of some very persistent chemicals eventually. It takes a long time, and sometimes because the chemical has to move into different parts of the environment to be able to be fully broken down, and obviously that takes a very long time. So very quickly I will introduce you to the most important biodegradation reaction, which is hydrolysis of an ester or of a carbonyl group. So let's have an ester. This just one ester group, so this will be our ester. It's got a carbonyl here, it's got an oxygen here. It comes from an alcohol. So if you're from biomaterials, you will know this. It comes from an alcohol and an acid, like this. So in this case, it's a different alcohol and acid. That's how we would make it, but how are we going to break it? So we need to break this by adding water. You can see that there's an H missing, and that there was an oxygen on both of those, and now there's only an oxygen between them. So we need to add H2O to this molecule to get it to break. Now we have to remember our organic chemistry from whenever you did organic chemistry. There are two possibilities. So let us let's do it with It doesn't work very well under neutral conditions. It's catalyzed either by a base or by an acid. So if we take base catalysis first, let's try that one. I'm not sure which one is easier. So if we take a base, OH-, that would be our base, and we push the electrons into the most positive carbon on here, which is this one here. That would be the most positive carbon. Goes in here, like that. That allows this oxygen to shuttle its double bond electrons onto here. That will shift the negative charge onto the oxygen, Let's resolve that first. So that will look like, and we need 4 bonds. So this is O, this is OH, and this is minus. And then the negative charge, whoops, I've run out of shot. Then the negative charge goes back in. Let me move it across a bit. Yep. Then the negative charge goes back in, like this, into the double bond, reforming the double bond. It's 2 electrons, so I need double arrow. That makes this carbon then have 5 bonds, which it can't do, so it's going to have to break one. In this case, we could kick the hydroxide back off again, but then we get back to where we started. So we'll kick the other one off, like that, which goes to this thing, OH. So we made the acid, and the only problem that we have is that our alcohol is deprotonated, so it has to move, it has to steal this proton effectively. Let's steal that one, like that, to make the product OH and O minus from this. Let us have a look at the acid catalyzed version immediately afterwards. So we had the acid catalyzed version, we're going to have to attack it with water. If you remember from organic chemistry, hydroxide is a fairly good nucleophile, it's quite good at attacking. Water is rubbish, it's a good leaving group, so it's good at going away. It's very bad at attacking because it's happy as it is. It's got a negative charge which it can donate into here, but it's not going to do that unless we've primed it beforehand. It's quite difficult to get that to work. So let's prime that beforehand by adding a proton to here. Whoops, H+. So the most protonizable group on here is this oxygen because it's got the biggest negative charge, and it can do it like that, which, let's resolve that one, makes us have this thing plus here, and now our water is good enough to attack that because it's now got a formal positive charge on it, right on the place where we want it. And so our lone pair, let me draw the lone pair as some eyes in there, maybe a ghost, is going to attack into the carbocation here, into the positive charge of our carbon, giving us this molecule. 1, 2, 3, oops, yeah, let's draw them. 3, 4, 5. So let's have OH here. This is OH, but it's got a positive charge on it, which is obviously ready to leave. And where was my oxygen? Like that. So now we need to resolve that. First of all, we can take this proton off. I'm going to rub it out because I'm run out of time. So that would give this molecule, and now we would like this to be removed. So we would like these electrons to go back in. It could be either of these are identical. So if we labeled these oxygens, we would be able to see that it's not always the same one. That becomes the double bond. It's not always this one, it's sometimes the one from the water. And we then get this being kicked out, and we need this hydrogen to go over there. So if we do that, we get the same product. We get 1, 2, this thing, plus, and obviously plus H+, but they obviously won't be formed as H+ and an and this deprotonated alcohol, I've forgotten the word for a moment, they won't be formed as that. It will transfer inside this molecule, or it will be protonated beforehand, depending on the conditions, and we will end up with an alcohol and an alcohol and the acid again. So we have two possible pathways. If we see it in neutral conditions, it is very difficult for the water to attack this because it's not positive enough, and the water isn't a good enough nucleophile, and the carbon isn't a good enough electrophile, so the reaction rate is very low. It doesn't mean it doesn't happen, it means it's very slow. So typically we would need either an acidic catalyst, that would be this one, or a base catalyst, or an enzyme which performs it in a slightly different way but analogous. I'm going to stop there because I need to get to something else.